Okay, kids, it's kind of late on Friday afternoon. I've been working on calendars and trying to plan for the next 6 weeks, which is a shot in the dark, but we'll give it a throw. I just sent that out not too long ago, kind of a calendar for how everything's going to play out. God knows that is subject to change, but at least you'll have some working idea. We got to get through circuits. We've got to get through magnetism. And then we've got to do some work on the atomic stuff. So we'll have that test over circuits, the test over magnetism, the test over atomic structure, and that it will not be an overall final. Okay, so let's just get that straight right now, that it will not be a big final at the end. Okay, so there's a couple of things that I want to go over on that assignment 22-3, even though you have the answer key. So if you look on question number 21, it's got a question about bulbs and voltage, and that always gets kind of weird. So on that initial state, it's got a 100-watt bulb is brighter than a 60-watt bulb when both operate at the same voltage of 120. So the whole key to that is that it's operating at the same 120 volts, which is what America runs on. And so if you look at kind of the math, and this is kind of the chicken scratch that I had. So if you look at the idea that power is V squared over R. So if you look at that 100-watt bulb versus that 60-watt bulb, okay? Well, they're both got 120 squared, and they've both got 120 squared on the top, okay? So the only way this can happen is if that 100-watt bulb has a smaller resistance and the 60-watt bulb has a higher resistance, which is, again, is somewhat counterintuitive. But if you look at this in terms of power that can be emitted from that light bulb, okay, well, that power is emitted from that light bulb. Then with that lower resistance, you can in effect put more of that energy into producing light and less of it going into overcoming the internal resistance of the light bulb. So that's just another way that you can look at this. So here's the deal. If we assume that the 100-watt bulb does have a lower resistance, okay, which it has to make this happen, then if you go to, now you're going to say what's going to happen is that, okay, hey, we're going to have the same amperage of 0.5 amps, then which one is going to be brighter? So then on that one, if you look at power equaling I squared R, okay, so if they have the same current, 0.5 or whatever it is, then the one that has the smaller resistance, okay, then is going to have the smaller power. So this is why it is so important that you look at what you're holding constant and what you're changing. So we established up here that if they have the same voltage, that means you have a lower resistance. Then with lower resistance with the same current will produce less power. Then that's going to be the one that is going to be less bright. And then the 60-watt bulb, which actually has a higher resistance, then is going to be brighter. So that's how that one's going to play out. Now, the other one that I kind of want to go over, which gets a little dodgy, is that question number 33. It's problem number 33. And it's got, the math gets a little bit weird. You've got a copper wire, 1 millimeter diameter, carries a current of 20 amps. What's the electric field strength inside this wire? So on that one, if you look at your electric field equaling delta V over L, which in this case is going to be the length of that wire. And so, well, your voltage, what we learned yesterday, is your current times your resistance over your L. But your current, when you look at that, is going to be the same. But then your resistance, instead of resistance, then we can put rho L over A divided by L. And then those L's cancel out. And then you get current times your resistivity divided by your area, okay? So that's where you want to look at this in terms of being able to freely do this substitution in terms of resistance and rho L over A. And then don't forget, even on that, since area is volume times length, and just a quick refresher and reminder, okay, you might want to keep this in mind, that when you look at that area, excuse me, I screwed that up. Volume is area times length. I got one step ahead of myself. So your area is volume divided by length. So if you look at that, resistance equaling rho L over A, and you do a little substitution, and you have rho L and then volume divided by your length, that flips up and you have rho L squared over your volume. So that's just might be something that you might want to keep in mind. Okay, so this last assignment out of 22-4, there's nothing really kind of hinky on it. I kind of chose those problems because it pulls together a whole bunch of different things. 46 is another problem where, ironically, it actually talks about a hot dog cooker. So now that you have a visual of how that looks with electricity passing through it, you can actually kind of get an idea of what that's going to play out. They actually give you the specific heat of a hot dog, which is, in case you were wondering, is 2,500 kilojoules per mole. Excuse me, per kilogram. My bad. Per kilogram. I don't know how someone figured that out. It's like, really? What's your research project? I'm finding the specific heat of a hot dog. Really? Okay. As opposed to like a marshmallow or a Dorito chip or something like that. No, I want the specific heat of a hot dog. Okay. Which is kind of scary because, a lot of that's water, and the specific heat of water is like 4,900. So anyway, there's that. They give you that problem, and you just got to do some calculations on that. Anyway, so today was pretty short. It was good seeing all of you today, except for, I think everybody ended up. No, we never did find Andrew. Anyway, but anyway, it was good seeing the rest of you and the random discussions that you guys have, and Catherine's wall of facts, not wall of fox. Let's get that straight. Anyway. Enjoy your weekend. I will be sending out the quiz tomorrow. Shouldn't be very long. Just going to kind of make sure that everybody kind of knows what's going on with these problems. Anyway, I will talk to you later.